Imagine you're aboard a spaceship, staring out at the endless void of space. The nearest star system, Alpha Centauri, is over 4 light-years away, meaning even if you traveled at the speed of light, it would still take 4 years to get there. But here's the problem. Our fastest spacecraft today, like NASA's Voyager 1, is moving at a mere 17 kilometers per second. At this speed, it would take over 70,000 years to reach Alpha Centauri. That's longer than human civilization has even existed. So, is there any way to break this barrier? Can we travel faster than light? And if not, are warp drives, the legendary technology of science fiction, actually possible? Today we're diving deep into one of the most fascinating questions in physics. We'll explore Einstein's laws, the concept of space-time manipulation, and cutting-edge theories that could make warp travel a reality. Buckle up, because this is where science meets the impossible. The speed of light, a cosmic speed limit. Before we even talk about warp drives, let's understand why the speed of light is such a big deal. According to Einstein's theory of relativity, nothing can exceed the speed of light in a vacuum, roughly 299,192 kilometers per second, or about 186,000 miles per second. Why? Because as an object accelerates toward light speed, its mass increases exponentially. If you were to push a spaceship faster and faster, the energy required to keep accelerating would grow infinitely. Eventually, you'd need infinite energy to reach or exceed the speed of light, something clearly impossible. But here's where things get interesting. Einstein never said space itself couldn't move faster than light. This loophole forms the foundation of warp drive technology. Instead of pushing a spaceship past the speed of light, why not manipulate the very fabric of space-time itself? Warp drives, how they could work. The concept of warp drives originates from science fiction, most famously in Star Trek, but it actually has serious scientific roots. In 1994, Mexican physicist Miguel Alcubierre proposed a theoretical model for a real warp drive, aptly named the Alcubierre drive. The idea is simple but revolutionary. Instead of accelerating a spacecraft through space, a warp drive would contract space-time in front of the ship and expand it behind, creating a bubble that moves the spacecraft without violating the speed of light limit. The ship itself wouldn't actually move. It would just ride the wave of distorted space. To visualize this, imagine an escalator. You're standing still, but the escalator itself moves, carrying you forward. Similarly, a warp drive would move the space around you, letting you reach distant stars faster than light, without breaking any laws of physics. But there's a catch. And it's a big one. The energy problem and exotic matter. For this warp bubble to form, it requires something physicists call negative energy, or exotic matter, a type of matter that theoretically has negative mass. This isn't the kind of stuff you can just scoop up from a planet's surface. In fact, we've never observed negative mass directly, though certain quantum effects suggest it might exist in tiny amounts. The amount of energy required for an Alcubierre warp drive is also astronomically high. Early estimates suggested it would take more energy than the entire observable universe contains, but recent revisions have reduced this requirement dramatically, though it's still far beyond our capabilities today. Could there be another way? Some physicists believe that if we find the right way to manipulate dark energy, the mysterious force accelerating the expansion of the universe, we might be able to use it for warp travel. Others suggest that advancements in quantum physics might eventually lead to the discovery of naturally occurring negative energy sources. But even if we solve the energy problem, there's another major issue with warp drives that could be even more dangerous. The dangers of warp travel. One of the biggest risks of traveling faster than light is what scientists call the horizon problem. When a ship moves at warp speed, it essentially gathers particles and radiation in front of it, like a cosmic snowplow. The moment the ship decelerates, all that energy is released at once, creating a blast of radiation so intense that it could obliterate everything in its path, including the destination planet. Another issue is causality violations, in other words, the possibility of time travel paradoxes. If a warp bubble moves faster than light, in some reference frames, it could technically arrive before it even leaves, leading to logical contradictions that physics doesn't yet fully understand. So, if warp drives are possible, We'd have to figure out how to prevent catastrophic radiation buildup and resolve potential time paradoxes, challenges that are just as difficult as the energy problem itself. But what if we don't need warp drives at all? What if there are alternative ways to reach the stars faster than light? Alternative ways to travel. Faster-than-light warp drives might be the most popular faster-than-light (FTL) travel concept, but they aren't the only possibility. Scientists have explored several other potential methods, some based on theoretical physics and others inspired by exotic cosmic phenomena. Could one of these alternatives be our ticket to the stars? Wormholes. Shortcuts through space-time. One of the most exciting possibilities is wormholes, also known as Einstein-Rosen bridges. These theoretical tunnels connect two distant points in space-time, allowing a spacecraft to travel between them almost instantaneously, like taking a shortcut through the fabric of reality. To understand this, picture a piece of paper. If you draw two dots far apart and travel between them in a straight line, it takes time. But if you fold the paper so the dots touch, you've created a shortcut, a wormhole. In theory, if we could stabilize a wormhole, we could jump light years in seconds. But as with warp drives, there's a major problem. Wormholes are incredibly unstable. The moment something enters, the tunnel would collapse instantly unless we could reinforce it with exotic matter or negative energy, neither of which we have access to yet. Plus, even if wormholes exist naturally in the universe, we'd still have to find one and figure out how to safely navigate it. Tachyons. Particles. That break the rules. Another idea comes from the concept of tachyons, hypothetical particles that are believed to always move faster than light. If tachyons exist, then in some exotic way they could allow for faster-than-light communication or even travel. However, tachyons have never been observed, and they may not be real at all. If they do exist, harnessing them for travel is a challenge, far beyond our current understanding of physics. Quantum tunneling. Can particles cheat physics? Quantum mechanics gives us another strange possibility: quantum tunneling. In certain situations, particles can seemingly teleport through barriers without actually passing through them in a conventional sense. If this effect could somehow be scaled up to macroscopic objects, it might offer a revolutionary new form of travel. However, as of now, quantum tunneling only works on a microscopic level, and there's no known way to apply it to something as large as a spaceship, the expansion of the universe, riding the cosmic wave. One fascinating fact about the universe is that space itself is expanding, and in some regions, like near black holes and in the early moments after the Big Bang, this expansion can happen faster than light. Scientists speculate that if we could somehow harness this natural expansion, we could travel vast distances without technically violating relativity. This idea is still highly speculative, but it aligns with some of the principles behind warp drives. Instead of moving through space, let space move around us. If we could create a controlled expansion bubble, we might have a way to move faster than light without violating the laws of physics. But while these concepts are fascinating, none of them are practically possible yet. The laws of physics still seem to prevent any conventional object from exceeding the speed of light, at least with our current understanding. So where does this leave us? Are we forever stuck with slow interstellar travel, or is there still hope, the future of faster-than-light travel? Is it really possible? We've explored warp drives, wormholes, tachyons, quantum tunneling, and cosmic expansion. But despite all these theories, we're still bound by the speed of light. Does that mean humanity will never travel to distant stars within a human lifetime? Not necessarily. While faster-than-light (FTL) travel isn't possible yet, history has shown that what seems impossible today can become reality tomorrow. Scientific breakthroughs, the key to unlocking FTL travel. Right now, the biggest obstacles are energy requirements, exotic matter, and stability issues. But what if future breakthroughs in physics reveal new ways to manipulate space-time? Just as quantum mechanics shattered classical physics, a deeper understanding of the universe might give us tools we can't even imagine today. For example, if scientists discover a way to create and sustain negative energy, warp drives and wormholes, might become viable. Similarly, new insights into quantum gravity or higher dimensional physics could open pathways we currently see as impossible. Even technologies like advanced antimatter propulsion could allow us to get closer to light speed, dramatically shortening travel times. The role of AI and advanced computing. Another key factor in solving the FTL puzzle is artificial intelligence. With AI-driven simulations and machine learning, scientists can explore millions of potential solutions at an accelerated rate. AI might help uncover hidden physics principles or optimize methods of space travel in ways human researchers would take centuries to figure out. Additionally, quantum computing, still in its infancy, might provide the raw processing power needed to simulate and test FTL theories far more effectively than we can today. Will humans ever travel faster than light? So, can we travel faster than light? As of now, no, but that doesn't mean we never will. Throughout history, humans have broken seemingly impossible barriers. People once thought heavier than air flight was a fantasy. Then came the right. Brothers, breaking the sound barrier was once considered deadly, until Chuck Yeager did it in 1947. Space travel itself was a science fiction dream. Until we landed on the moon in 1969, the speed of light might be another barrier, but barriers are meant to be broken. The biggest question isn't, is FTL travel possible? It's, how long will it take us to figure it out? Final thoughts. What if it happens? Imagine a future where warp drives or wormholes are real, where humanity spreads across the stars, where a journey to another galaxy takes hours instead of thousands of years. If FTL travel ever becomes possible, it won't just be the greatest scientific breakthrough of all time. It will change the destiny of our entire species. So what do you think? Will we one day break the speed of light, or is it an unbreakable law of nature? Let me know in the comments. And if you enjoyed this deep dive into the future of space travel, don't forget to like and subscribe for more cosmic mysteries. Until next time, keep wondering and keep looking to the stars.